In this mini lecture for Module 10, we're going to be working through an example of a Pearson correlation. So imagine a scenario where a hospital administrator wants to examine the relationship of how individual patients are going to self-rate their health to the number of physician visits that they've made in the last year. So when individuals are self-rating their health, we have a scale from 1 to 5, where 1 would be poor health and 5 would be excellent health. So we have a number of patients. Here's an example of 8 different patients and their value for their self-rated health on this scale, and then information on the number of physician visits that they've made in the last year. So for each of the individuals, we have a record for their health and the number of visits that they have. We can take this information and put it into a scatter plot, where on our x-axis here we have self-rated health, and on our y-axis we have the number of physician visits in the last year, and we get the sense that there's potentially a negative relationship. One very important thing to note with correlations that we covered in the last module is that correlation is not causation, right? We're just looking at the association between these variables, so we could switch them and have physician visits on the x-axis and health on the y-axis, because we don't have a true sort of independent and dependent variable when we're doing a correlation, because we're just looking at how these things are associated. So it's not how does one thing cause a change in the other thing, because correlation is not causation. So here with the scatter plot, again, we sort of see that there's a negative relationship, but we want to know a little bit more. So we can actually calculate a correlation coefficient, and this is done quantitatively. So the Pearson correlation coefficient, which is symbolized by R, is a quantitative measure of the strength and type of association between two continuous variables. It ranges from -1 to +1, so a perfect negative relationship to a perfect positive relationship, and a value of 0 means that the two variables are not correlated at all, so there's no relationship between them. Because as you change whatever's on your x-axis, there'd be no corresponding change in y if our correlation coefficient was equal to 0. And the idea with doing this quantitatively is that we can do better than just looking at a scatter plot and having some qualitative sense of what the relationship is. So we're going to walk through a correlation example. And this example I'm going to walk through, there's a lot on here, but we're going to go through it a little bit at a time. And this is a slightly different method than the two that are presented in the book, but it's exactly equivalent. So the numbers would work out exactly the same, just in terms of explaining what's going on in a Pearson correlation. I thought this would be a better way to do it. So here we have our data. What you can see are the patients from 1 to 8, their self-rated health, which we put on our x-axis, and the number of physician visits in the last year, which we're just calling y for this, because we've got to do all these calculations. We need to keep these straight. So the first step that we're going to have to do, I'm going to show you the full equation after we walk through this table. The first thing we're going to do is we're going to calculate the means of the self-rated health, so that's x bar, and the number of physician visits, which is y bar. So we have that data. The next step we're going to do is we're going to look at how each of the values for the patients differ from the overall mean. So that's our next two columns. So it's x, the value for individual 1, which is 5, minus the mean, which is 3.75, will give us a value of 1.25. Some of these are going to be positive, some of them are going to be negative, just depending on where they fall relative to the mean. Okay, so we have our deviation scores. The next thing we're going to do is we're going to take our columns of our deviation scores for their x, so health, and the physician visits, which is y. We're going to multiply those two together. That gives us our next column. Then, in the last two columns, what we're going to do is our deviation scores, and we're going to square them. So x minus x bar squared is going to be in the second to the last column, and y minus y bar, and then squaring that is in our last column. And these ideas of calculating deviation scores and squaring deviations are all things that you've seen in other calculations that we've done in earlier modules. Then the last thing that we're going to do here is we're going to sum up these last three columns. And the last two columns should look pretty familiar because you're summing up the squared deviations So that's like a sum of squares, and you've seen that before. So based on all these deviations, we are actually going to look at how we calculate our correlation coefficient. And here's our formula. Again, I think this is a simpler formula to sort of wrap your head around compared to what's in the textbook. Again, they're all entirely equivalent, however. So in the numerator, we have the deviation scores of our x variable, whatever we're calling x, and whatever we're calling y. So those deviation scores multiply together for each individual and then summing those up. That's in the numerator. And then the denominator is looking basically at the sum of squares for our x and y. And we already have these from these last three columns. That's all the information we need, is the summations from those last three columns. So we just put those into our equation, and we'll get a value of negative 0.808. And when we look at our plot that we had before, at our scatter plot, so our value of our correlation coefficient for this would be negative 0.808. And when you look at the data, there's a negative relationship there as well, and those data points would fall quite closely along some line that would be drawn through them. So that's our value of our correlation coefficient, but if we wanted to actually test this statistically, well, we'd have to figure out what's our statistical hypothesis. So how do you know if the correlation between the two variables is statistically significant? Well, our null hypothesis is that rho, which would be the population level correlation coefficient, is equal to 0. And our alternative hypothesis is that rho, again the population level correlation coefficient, is not equal to 0. And we have r as our estimate of rho. This is going to be tested using the t-distribution and a one-sample t-test. So when we calculate t, it's going to be our value of r minus 0, because in our null hypothesis we're comparing it to 0. And then we have a value of the standard error of r. And here's the formula for the standard error of r. And again, we just plug in our values because we know what r is. Our n is the number of individuals that we had. So we had 8 individuals. And here's the calculation. So we know that our value of r is negative 0.808. So we plug that in. We know that n is equal to 8. We plug all this in and we get our standard error of r is equal to 0.241. So our value of t then is r minus 0 in the numerator, which is just negative 0.808, divided by the denominator, which is the standard error of r, which is 0.241, and we get our t statistic of negative 3.353. Our degrees of freedom are n minus 2, because we have data for our value of x's that we're using and our values for y. So the self-rated health and the number of physician visits, so it's n minus 2 because we had to estimate means for both of those. So our degrees of freedom here is 8 minus 2, which is equal to 6. And you just go to the t-table and look it up like you always would and get your critical value of 2.447. And this is a two-tailed distribution. We can put in our critical values. Remember that the rejection regions are in the tails of those two. And our t statistic is negative 3.353, so it's going to fall in the rejection region associated with the negative tail. And because our absolute value of our t statistic is greater than our absolute value of our critical value, we're going to reject our null hypothesis and conclude that the population level correlation coefficient is not equal to 0. And we found that our correlation coefficient in this case is estimated to be negative 0.808.